Hi, welcome back. Recall from last time when I was going through the Dijkstra algorithm, I kind of mentioned the fact that I like to keep this mental image of the algorithm of me being like an explorer on the graph, where I want to find the shortest path between where I'm currently at to every other possible destination of this graph. And I like to use this mental image a lot because it helps me not only remember how Dijkstra works, but also how to make the connection between Dijkstra and a very similar algorithm like A star. Okay, so it's really easily extended to this algorithm. And more importantly, it helped me distinguish the two algorithms a lot easier as well. And so A star is, in a sense, very, very similar to Dijkstra because one, they both have a starting vertex, and two, they both uses like this fringe slash priority queue data structure to help us keep track of which vertex to visit next, depending on whatever priority you made it to be. And the main differences between them are one, A star has a goal vertex. And so what that means or how that translates into the mental image is that instead of trying to find a shortest path between where I'm currently at to every single other possible destinations in your graph, I have a specific destination in mind. And so that will be my goal vertex, right? And so instead of trying to find a shortest path between this and all of the other vertices in your graph, I only trying to find a specific shortest path. And that is the shortest path between the starting vertex to the goal vertex. And so what A star does is to incorporate this information into the algorithm, and specifically using something we call a heuristic that kind of help us guide towards the goals, meaning that when we're exploring the shortest path, we are moving in the right direction instead of kind of go over all over the place and finding shortest path there and wasting energy and time when we know that, okay, the goal is probably over here. And so I'm going to dive into the heuristics component of this algorithm in more detail in a later slide, but keep in mind that's kind of what heuristics does in its algorithm. And another main difference between A star and Dijkstra is that because instead of finding a shortest path, many shortest path between the starting vertex to the other vertices in the graph, I'm only finding a specific shortest path, then that means we probably want to tag our vertex differently, right? Meaning that we want to use a different priority for each vertex. And specifically, that priority has two components. So instead of just having the distance already traveled, so that's your dist2 value, you also add the estimated travel distance between this current vertex you're looking at to the goal vertex. And this estimated travel distance is a value that heuristic will provide you. And so this will be our new priority to help us know, like, first of all, keep track of which way to move will be the shortest path, and also which whether or not this shortest path is in the right direction relative to the goal vertex. And so the second component of estimated travel distance in the future incorporates that information, because if that value is small, that kind of tells me I'm probably at a vertex that is very, very close to the goal vertex. And lastly, because just as a natural consequence of that, because we are not finding the shortest path between the starting vertex to all of the other vertices in your graph, not every vertex will be visited, and you'll see that in examples and demos. So I have highlighted the result here between of the A star algorithm, and that is it is not finding a shortest path tree of the starting vertex, but rather it is a specific shortest path. So this is a very important distinction, because for Dijkstra, you're finding multiple shortest path, right? You're basically finding all possible shortest path between the starting vertex and all of the other vertices in your graph. But for A star, it is not the case. And so it's important to keep that in mind. Okay, and so with all that components and also the connection we made to Dijkstra, I'm just going to quickly go over the high level overview of the algorithm again. And so what we do is that you first initialize a priority queue with all of initialized values in it. And then you follow this very, very similar process as Dijkstra, where you pop the node from the front of the queue. And as you do that, you add the edge to edge into your shortest path. That's under construction. And then you check if you need to update the priority or the dis to edge to values for all of the unvisited children in the current node. So this is still under the assumption that we are running A star on an undirected graph. And also the priority queue will be resorted automatically. And step 6 is very important. That's why it's bolded here. This is the key difference in the algorithm itself that is different from the Dijkstra algorithm. And so step 6 denotes the stopping condition for A star, right? So instead of stopping when the priority queue is empty, like in the Dijkstra case, A star stops when we've hit the goal node. So we just stop immediately if we have visited the goal node in whatever our goal vertex is. And that makes sense, right? Because we know that the whole purpose of A star is just to find the shortest path between the starting vertex and the goal vertex. And so as you kind of repeat, if you haven't find the goal, like visit the goal vertex yet, you repeat while the priority queue is not empty. So I hope all of this makes sense. And also I also linked the Hug's magical demo of A-star algorithm here. And so if you want to refresh on the specific details of A-star algorithm, please refer to this demo. I did not include a demo in this mini lecture. So for what the main reason that it is very, very similar to Dijkstra in terms of how it updates values and stuff like that. And so if you want to kind of brush up on the specific details of this mechanism, just go to this demo and run through it, internalize all of these details. Okay, so the last topic I would like to cover about A-star is the heuristics, which I think is the most fun part of this algorithm. And so relating back to that mental image I kind of described to you guys, how I like to think of the heuristics for A-star is that it's kind of this tour guide buddy that travels with you as you are exploring the graph. And what I mean by that is as you're exploring the graph and you are at a certain vertex on the graph, your job is to kind of keep track of what you did so far. So how far you've traveled, which is like the dis2 value, right? And the tour guide buddy kind of looks ahead as you're doing that. It looks ahead and kind of estimates how much you still have to travel. So it kind of tells you, okay, I think from this position, you probably still have to travel like 60 more miles to reach the goal. And so that's basically all it's doing. It's telling you how much more distance you might still have to travel to get to the goal. So it's as a partner, as your partner, and together you guys kind of figure out and construct this new metric or priority, like I kind of mentioned in the previous slide, to judge whether or not this vertex is a good vertex or a vertex that should be visited or added into the shortest path tree. So that's kind of the main role of this heuristic or this tour guide buddy here. And like any person in life, right, you can't fully trust that person unless you know that person is good or trustworthy. And in real life, you probably have like very different criterias depending on who you are to judge whether or not a person is good. Like for example, I kind of judge first of all, like if a person is good or trustworthy, depending on the fact if like they're a fan of Taylor Swift. But you know, like I can't use that criteria in this case, right? But the key idea is that this kind of notion is relevant to how you understand what a good heuristic is. And so what a good heuristic or a good tour guide buddy or trustworthy tour guide buddy is that it satisfies two properties. And they don't necessarily have to be, this is like an either or relationship. So it doesn't mean like they have to satisfy both to be good. At least one of them is sufficient. And specifically, these two properties are admissibility and consistency. And these two are big words. I know it's kind of confusing to think of them and it's hard to kind of distinguish them. So I kind of drew this diagram down here to help you visualize what that means. And so if you kind of imagine that from your starting vertex to like your starting point to the goal point, you have like a path, right? And imagine stretching that one out as a linear line here, like kind of drew here. And you're at this current vertex and you want to kind of see how far you still have to travel to reach to the end. And so to the left side of this vertex would be the distance I've traveled so far to get to this place, which means it will be your dist2 value. And to the right of that, in this black bolded line, that is the exact distance that you still have to travel to go from your current vertex to the goal vertex. So this is the exact distance. And a heuristic is always an estimation, right? And so an admissible heuristic, which is labeled blue here, it always underestimates the total travel distance. So this black bolded line, it is the total travel distance that you still have to make to reach to the goal from your current vertex. And notice that this blue line here, which is what the heuristic estimates, is an underestimation of the goal vertex. So means that it is shorter than the exact, shorter than or equal to than the exact distance between the current vertex and the goal vertex. And so that's what a admissible heuristic is. And on the other hand, for a consistent heuristic, instead of thinking this distance that you still have to travel as one big chunk, you kind of divide that by into these like little chunks by viewing the vertices that you have to visit along the way as intermediate stops or kind of different steps you have to take. And so instead of viewing it as one chunk, you're viewing them as individual steps. And then for each step or the distance between each stop, the consistent heuristic always underestimates that distance. So notice that these little orange chunks you have down here, these always underestimates their corresponding distance between the stops, right? And, oh, sorry. And this is what consistent heuristic does. And a very cool observation to make is that if you stitch these little orange chunks together, you notice that this distance is guaranteed to be less than the total distance you have to travel, meaning that a consistent heuristic implies that it is also admissible. Or if you know that a heuristic is consistent, it guarantees that it is also admissible. But the other way around is not necessarily true. And the reason for that, I'll leave it for you guys to kind of figure out on your own for exercise. And a good like general guideline on that to figure out the exact reason why it doesn't work the other way around is to utilize a visualization that is very, very similar to this one and think about why it is the case that a heuristic is admissible doesn't necessarily mean that it is consistent. So that's all of what I have on reviewing the A-star algorithm and Dijkstra. I hope you guys found this video helpful. And yeah, good luck studying.